Hi and welcome everyone to our presentation on DIY Robot Overlord. I'm Meredith.
I'm Paris.
I'm Tim.
I'm Mars.
And we've got John hiding behind the cameras.
John's out in the field.
So we're from Tasmania, which has better coffee and better internet than Melbourne, which is why we decided not to go to Melbourne this year to present at PAX.
And the only reason.
That's the only reason.
So please note this presentation. It includes depictions of eight-legged creatures. They happen to move in a pretty spidery fashion, so we wanted to let you know in case anyone's afraid of spiders ahead of time, you might want to switch off now.
Apparently the fear only kicks in with our spider when you see it moving, not when it's still. So
True.
Just turn away appropriately. We'll try and give you a warning, but it's the internet, so you can just fast forward.
True.
Okay, so let's begin. We're here to talk about artificial intelligence. Specifically, we're going to be talking a little bit about proximal policy optimization. We're going to be referring to this as PPO from this point onwards. This is actually a pretty standard gradient descent optimizing sort of algorithm. The main thing I really want to talk about here is epsilon. Epsilon in this case is the hyperparameter. You're probably going to want to set that around, I reckon 0.1, 0.2, somewhere around that.
This is much simpler than they used to.
Yeah, it's the opening slides. We're going to start slow and then work into the actual problem out. No, we're just kidding. The maths that we're going to get about as complicated is our good old-fashioned stonks. Hopefully we can keep it this sort of simple, but we'll work it out.
So here's what to expect in this talk. So we've got giant working robots.
That look like spiders, we're sorry.
Exactly. We have laser guns, which is very cool. We have explosions and numbers and computer science and graphs or graphs?
This is a worldwide audience now. So graphs and graphs.
Take your pick. It's graphs.
Only Tasmanians think it's graphs. So now the Melbournians will know.
Oh,
and the world.
Yeah, but they pronounce things a bit weird. Hasn't it said Mal before?
I'm from Melbourne.
Oh, okay. So, and we also have humanity defeated by the machines and more graphs.
Graphs.
Graphs. So let's get started for real. So what do we think about when we think about AI? Well, you probably think of things like this. Robot characters in films, good or bad. They squeak or they beep or they have guns for hands. Mm-hmm. We think of beloved characters such as Claptrap. Beloved.
Is Claptrap actually beloved?
Yeah,
it's beloved by you.
Yeah, of course he is.
We have the Reapers for Mass Effect. There are lots of places
Definitely beloved.
robot characters. On a side, I have a whole rant prepared about how robot characters are usually just like arbitrarily robots and it doesn't have any impact on them except that it gives them particular abilities or it's just a plot point. Like they're very little explored as much as they could be and they're usually very human-like in their abilities and how they act.
Very true.
You also get things like this online where you see like people on Twitter who are like, I made an AI watch Olive Garden commercials for 4,000 hours and make them generate some content. So you'll see these things that are like comically kind of nonsense or, they're playing off something that is proposed to be absolutely random absurdity. But none of these are AI, particularly in the case of the menu thing where most of these have turned out to be completely fake. There are a couple of people who actually do this stuff like Janelle Shane. On Twitter, there are a few people who are complete experts in making generative content, and it's a really interesting field, but most of the ones you stumble upon are fake. So when we think about AI, what we're talking about today, it's usually more like a collection of algorithms that solve a problem.
And graphs.
And graphs.
Graphs.
Well, in the way that we make them digestible to a human, they are graphs, yes. Mm-hmm. But generally, if we thought about this AI, as you would see in Claptrap or something, that would be thousands of these systems as we have them today. They're usually made to solve one problem, like recognize whether that's a bicycle or a person in an image. They can't also tell you on a 3D plane where they are. They're usually very discrete problems, trying to replicate what appears to be a human skill, but they don't have human context. Very closed. They're not as powerful as lots of news headlines would make you believe.
So they're definitely not always reliable, essentially. Cool. So this example is fantastic. I just love it. The pattern of noise was overlaid on this image of the cat. the AI decided that it was actually guacamole.
Because obviously this cat looks a lot like guacamole.
Totally. Yeah.
This is a really interesting example because it sort of shows how these AI work without actually really explaining how they work. And like that is clearly a picture of a cat. Like we clearly have a cat there. But just by adding a literal noise pattern, like if you actually do a subtractive image, it's a bit annoying to do it. But if you look at it, it's actually just little speckles, like little speckles all over the cat. There's nothing actually there that no longer makes it a cat. But as soon as you do that, suddenly it's guacamole. And the AI can't tell because those weird little dots suddenly make it guacamole.
This is not like a magic
cat.
guidebook where if you squint long enough, you will see the guacamole in the cat.
No. And they only rotated a little bit, right?
Yeah.
So,
Yes. If you rotate it just a little bit, you can trick it into thinking one way or the other.
But there's lots of examples where you can perturb an image slightly and then AI thinks it's something completely different. It's very, very common because AI is actually really stupid.
Well, it's interesting because the way that it's stupid is it's recognizing edges. So if you feed it a million pictures of cats, it will recognize usually they've got some points, they've got some curves, and they've got some orbs, and that will recognize as a cat.
I think we call them eyes normally, but
it doesn't know what an eye is. So
orbs.
It's quite interesting because you can do the opposite. You can get a neural net that's been taught to recognize something, and you can feed it nonsense data until you can get it. You can kind of brute force it into giving you a result of what it thinks the most cat thing is.
Yeah.
And it will just be like a bunch of ears and eyes and stuff that we don't even recognize. But that's what it thinks cat is.
Yeah.
And so the thing that it thinks is most guacamole is probably something that's totally nonsense to us.
Yep.
This is very young.
So, should we move on? We've talked about the guacamole cat enough. You can tweet guacamole cat hashtag if you're interested.
Yes, guacamole cats. Let's talk about how AI in games generally works. The human site that sits there and then writes down the rules for what to do when. You could effectively sit there and read the code and figure out what it's doing.
Just a list of rules.
Yeah.
So you hear an explosion over there, run towards it, the player's probably over there, shoot towards them.
Yeah.
So, by contrast, what we're going to be doing today is not just a list of rules. So there's a whole domain of rules-based AI, which is a thing that kind of slowly died out once computer scientists found something new and shiny to play with. The new and shiny thing to play with is artificial neural networks and the associated domains with them. And this is mostly what production AI, so AI that you'll see deployed in the real world, everywhere from like airport X-ray machines to video games.
Even in the phones you carry have hundreds of
Your
AI.
photo gallery in your phone learns what your cat looks like from using neural networks. And so most real-world production AI, including video games, involves training a neural network to do something. And that's pretty much what we're going to be doing today.
Yeah. So we're going to be talking about artificial neural networks, which are meant to be evocative of how actual neural networks work. They're a little bit different in that they sort of took inspiration from them, but then sort of threw away all of the nuance and made them their own sort of thing. But at their core, they're inspired in a similar sort of way. So in your brain, you've got, I believe it's billions, might be trillions of neurons inside your brain. Trillions, there you go.
Yeah.
He's got mega brain. He's got big brain energy. I've got small brain energy. So you've got these billions or trillions, in Paris' case, of these neurons all sitting, and they're all interconnected together. So you've got this sort of like lovely little picture of a neuron there, and you got these like little,
Scientist,
Yeah, it's a science.
Meshed together like those ships from Guardians of the Galaxy 1.
Yes, meshed together like those ships from Guardians of the Galaxy 1. Thank you, Mars, for that description.
Fabulous.
The one that Peter Serafinovich is flying and leading.
Yes.
Yes. Yeah, it is. Trust me, it is.
Yeah, no, it's Peter
I'm going to be correct on this. You don't have to argue
Pie
with me.
Maker's bad guy.
Yeah.
Dance battle?
Peter
Lead
Serafinovich
pace.
is one of the good guys.
Okay.
Maybe.
So you've got these very large complex neural networks, which is just a giant mesh of interconnected neurons. And basically, at some point, the neurons connect up to various different things. You might have neurons which connect to your eyes and neurons which connect to your hands and so on and so forth. And by feeding certain input, the mesh sort of works it out. The network resolves and it tells you to do things. So by looking at something, you can see how you're going to sort of move over there. You get enough of these neural nets, you make them big enough, and you get a brain. You get something of human intelligence, sort of. We're really sort of going very, very high level and skipping over a lot there because it's not really how neural networks work currently, and we're not biologists, so we don't really want to go into that. It looks foolish. But what we're going to be talking about is we're going to be talking about artificial neural networks and the three main things we really care about there, which is actions, observations, and rewards. So actions are what you can do, i.e. move your arms and legs. Observations is what you know, so you know your eyeballs can, you can hear things. Rewards is what you get when you do the right thing, which, as in all things, is sweet treats, both for AI
sweet treats.
and for real life. So basically, observations get fed into the brain, which gives you actions. Performing the right actions gives you a reward. And what you want when you're an AI is the most reward, just like when you are a human. So the computer, see, exactly. The computer then uses that big, long, complex proximal policy optimization formula and other sort of similar ones to sort of crunch it in and give you the right sort of results for that. That's where the maths comes in. We're not going to talk about that at all. So realistically, an AI is this. It's getting a computer to solve a repetitive task with only minimal guidance. We basically just set it up, push it over the cliff, and see if it figures out how to fly.
And we hope it does most of the time.
They're
let's make
reward
an AI.
maximizers.
This is where you need like confetti cannons. Let's make an AI. We're going to do it here on stage, live right now. It's going to be very cool. We're going to train an AI who is John out in the field. And we're going to teach him that he should walk forward and reach a goal. The way that we're going to do this is with rewards, like we said before. So we're going to say that if he moves forward, we give him a treat. And if he moves backwards, we take a treat off him.
Might walk forward. Have a minty. Thank you. Ah, brilliant. Oh, I might take a step backwards.
Oh, bless his little robot heart.
Give me that minty back.
Oh,
So sad.
Guess I'm walking forward. Have a minty. Yay!
That was incredibly easy, and not at all degrading to John, who was an absolute professional scientist and game developer. We didn't degrade him even slightly.
Not at all.
But
not
it was
at
easy.
all. It
So-
was easy.
It's very easy, actually. Yeah.
Now John can do two directions.
Forward and back.
Except one is bad.
One is
That's a good point,
One is
yeah.
definitely bad.
He'll only ever go forward. But is this not a life lesson?
It is.
Only go forward.
Definitely.
Going back is
taught John to
bad.
go forward.
Yeah, that's great.
Absolutely. But we've done that, so we know how to make a thing move. Sorry, John. Move forward. So let's see if we can make that work in an actual game then.
Okay, good.
Okay. All right, okay, so what we're going to do is we're going to do a few sort of things here. What we're going to do is we're going to sort of recreate that experiment as we just had it out in the field, but we're going to do it on a laptop here. The way we're going to do this is we're going to follow these 4 steps. We're going to make a virtual environment. We're going to be doing that in a game tool. We're going to tell the robot some facts, so the things it knows, i.e. its position, basically. We're then going to make the robot do things based on actions, and then depending on how well it performs those actions, we either reward it or we punish it. So that's basically what we're going to do. Now for that, we're just going to cut straight to a demo, and we'll get cracking here.
This is our game engine.
So this here is this is our software. Well, this here is Unity, which is a pretty popular. I believe it's still the most popular game development tool. I'm not quite sure the exact numbers. Very popular game development tool. What we're using here is we're using a little bit of software called the Unity ML Agents framework, which is written by Unity specifically for creating machine learning AI. We're not going to be doing anything too fancy here. I just sort of wanted to roughly talk about it so that when we sort of start pointing different things out, you're not like, wow, what the hell's that? So what we've got is we've got our scene here. This is our virtual environment. We've got 2 main elements here. We've got our little robot here.
Which is John in this context.
This is our John equivalent. John Bot.
His name was Little Beeper.
Little Beepo. John Bot, Little Beepo. Is there a difference? There is. John's a lot more complex. And then,
John's a computer scientist.
Sorry, John.
how do you know Little Beepo isn't? Wow, way to crush him before he's even got
We've degraded
started.
John and the robot.
Yeah, wow, jeez. All right, and then the other thing in our scene here is this little orange cube. And the orange cube is the goal for our robots, because robots, as like humans, the true goal is to reach the orange cube. Yeah, so that is going to be our goal. So much like what we had with John, where he got rewarded when he moved further forward, basically the closer our robot gets towards the orange cube, the more rewards it will be given. Now, if I just run this as is, nothing will actually happen because it hasn't got a brain.
Pretty sure he just freaks out and slows
So what he's actually doing here is it's basically completely freaking out and going backwards. I'm just going to stop that because it's mean. We don't want to torture the poor little guy.
I'm out.
He's basically going like, nope, life sucks, I'm leaving. I believe he'd actually fall off the edge if he kept going back. And
If you were faced with a giant orange cube that you didn't know where it'd come from, you would probably back slowly.
I would back away.
at the very like,
It was glowing.
yeah, but you got to remember, there's something they're taking
also
away
if you
minties
just
as you're
woke
doing
up-
that.
new to existence in a featureless void with nothing but the cube, you might intuit that maybe the cube is relevant.
At the very least, you would realize the cube has something to do with it. You'd give it a
You
go
already have a
anyway.
brain, so it's
Yeah,
not a
that's true.
comparison.
So, going back to our little robot here. Basically, it doesn't know what to do. It's confused. It's basically making random actions, and purely by chance, the random actions in this case was to go backwards. So what I'm going to do is I'm just going to make a couple of quick little changes here. I'm now going to sort of show how you can actually train one of these. And we're going to be using a tool called TensorFlow to train it. TensorFlow is the
industry standard
It's
for
the
AI.
standard for AI. It's got a very silly name. Don't worry about it, TensorFlow.
It's the big Google energy of ML.
Literally made by Google, actually, yes. So it is the big Google
It's a
energy.
very popular framework that AI developers use to build AI tools in the real world. It's used from everything from video games to the back end on websites to recommend you more things to buy. It's used by everything. It's so popular, it's the de facto standard.
All right, so let's get training. So what I'm going to do is I've got to do a few things here. We do have to do a little bit of stuff in terminal. Don't worry, it's not going to be too much. If you're not really comfortable with ever doing command line stuff and you do want to get into AI, you are going to have to get comfortable with doing command line stuff because there is a lot of command line stuff in AI. But it's not too tricky for the most
this.
part. For this, it's pretty straighthtforward though.
For Unity ML though, like if you were doing like Python or something, that's just
If
you're
you're
scaring people.
If you're
You
interested in
don't
learning-
have to do Python.
If you're interested in learning how to do this on a technical level,
Yeah.
we will tweet some links out while this presentation is
That's a
going
good
out
idea.
during PAX, so you can learn how to do this.
But also Unity ML, I hate it when you call it that. The Unity ML Agent Framework
Toolkit.
is quite new. Toolkit is quite new, and with every release they actually pare out more of the manual things that you have to do on the Python side. So pretty soon you'll just be like, I would like this car to drive, please, boop, and it will go.
Awesome.
Because there's already much less than there was to do on that side 6 months
Yeah.
ago, and now you just run.
I'm going to go back to the demo now.
Yep, all right,
All right,
go.
we'll go back to our demo. Okay, here's our lovely command line. I'm going to press enter. This is a big long thing. It goes, hey, basically start training. We wait a brief second because it's gonna, oh, there we go. So this is now waiting for me to press play. I'm just gonna go over here and press play. I did not turn on control.
So because we don't know what we're doing, we're going to change a few things in Unity.
We thought we would
Just
go
gonna
live
stop
demo.
that.
Live demo, even though, you know,
This is computer science.
computer science is lots of like, I forgot to push the button, and now the long running process that I just started is completely ruined.
Control.
I just love that one of the longest running issues on the ML Agents framework GitHub repo is one guy who's got his Unity logo in ASCII prints out crooked because he doesn't
Yeah.
have a fixed width font. And
Yeah.
it's just like Unity employees being like, just change it, man. He's like, but I don't want to have to.
By the way,
Moving on.
so cutting back into here, so I'm just going to press play. And what this is now doing is Unity and TensorFlow are talking back and forth to each other. It actually looks really jerky and it's doing all kinds of weird things. That's because it's actually running at like a gazillion times its normal frame rate. It would normally not be going anywhere near this fast. It's going this fast just because it's easier to train it at hyper speed than it is to train it at sort of human speed. We don't need it to.
Even though this robot and this cube are visualized for you, the visual elements are not necessary for the simulation that is being used to train the AI.
Also, it's worth saying that these little sparks are actually like confetti that happens when it hits the cube, which tells you how fast it's achieving that.
Also, it's worth pointing out, this is really what machine learning is all about these days.
Graphs.
It's looking at your graphs from TensorBoard. Now, if you are sort of interested, we can, talk about this sort of stuff at some point in the future with you. But basically, this is sort of showing
This
how
is on
smart the
Rewards good,
robot
loss
is.
bad.
Yeah, how much of the rewards good, loss bad the robot's getting. Specifically, there's sort of one here which I think is sort of obvious looking, which is basically this cumulative reward one. So it's sort of creaking up here a little bit over time, which really makes sense with what we would expect, because as the robot's sort of learning, initially it's making garbage moves because it doesn't understand anything. It's just sort of going back and forth all over the place. But as it starts getting better, it starts sort of learning very quickly, oh, I should go forward and then just keep going forward. So it sort of really rapidly learns and then sort of caps out. And that's actually what you would expect to see. You would expect to see the AI suck at first, then suddenly work out, get over some sort of mental robot hurdle and then crush it straight on through to the edge, because that's how robots work apparently.
So much like John in The Void, he would have appeared, not knowing what he was supposed to do, stepped forward, gone, okay, I've got a reward, tried to step back, not knowing if that was different. But even then, just because you got a reward once for stepping forward. Maybe it was towards something that used to be over there, but now it's not. You don't know that doing it again will do the same thing. So they're quite tentative to begin with.
Because the robot's only goal in life is to be rewarded, and the only place it can get a reward is the cube, what is effectively happening is the robot is spawning into this featureless void. It's rolling a completely random dice as to decide whether it goes forward or backwards, and then it's getting punished if it goes backwards and rewarded if it goes forwards. As it goes forward more often, it slowly removes signs from the dice that tell it to go backwards, basically. So it rolls the dice repeatedly until it's only going forward, and it's learned to successfully do that. That's effectively what the robot is doing. Because a lot of people asked us, is the robot just taking random actions at the beginning? Yes. The actions the robot is taking at the beginning are totally random until it is slowly reducing the pool of actions it can take to only being the ones that get it the reward. Okay, so now that we've trained our little robot to go forward, we're going to take the output of that training, which is basically our brain, and put it into the game engine and turn off the training process and then let the brain just run the robot, which means the robot should basically just go forward every time it spawns.
This here, this little file here is actually the thing that got trained. If you're sort of curious, it's a sort of predefined format inside TensorFlow. You don't really have to worry about it too much.
How many kilobytes is it?
It is 71 kilobytes.
So it's 71 kilobytes of knowledge to go forward.
Yeah. You could probably actually make it a little bit smaller than that with some optimization.
But
But so what I'm going to do is I'm going to drag this into Unity. Then here I'm just going to sort of make a couple of little tiny changes here. And then I'm going to click play. And now using our lovely pre-trained robot,
Yay!
he drives forward and correctly gets the cube.
Look at him go. He's unstoppable.
Wow.
Great success.
Unstoppable.
So he's basically optimized to go forward and get his little reward.
He's very good at it though, and that was actually trained in real time. So that took what, about 3 minutes, give or take, I would say roughly, to sort of train.
Highly recommend learning how to do that yourself, because if you watch it train and if you gave it its brain, you feel very enamored with it. You get very endeared, and you're personally invested when it succeeds.
If you're watching this and you have ever made anything with a game engine, even for a couple of moments, even if you spawned a cube and were pleased with yourself, that's fabulous. You have enough knowledge of Unity to be able to do this.
Yes. And when you give something behavior, it feels very much like it's your little baby robot.
Okay, so let's now go back to our slides and talk about what we just saw. Because actually,
Demo over.
we could actually have made a better version of this AI using the old rules-based system, which we mentioned earlier, and that rule would basically be hold down the forward key, go forward. We could have saved a lot of time, work, and we could have solved Tim dragging things around in Unity, and just made a program that drives the robot straight forward all the time, and it would have reached the cube and everything would have been fabulous. But we didn't. So we're going to try something slightly more challenging this time, and hopefully expand your mind a little bit. We're going to make John, who is out in the field for us, drink a glass of water. Right?
Revolutionary stuff.
This is actually quite a complex thing.
This is more becoming of a computer scientist.
This is not funny. Drinking a glass of water is complicated. Like human children who have full use of their arms learn to do it quite slowly, actually. It's quite a complicated
I
task.
was going to say, any animator in the audience would know.
What
What do you mean, just drinking a glass of water? It involves fingers!
Drinking a glass of water involves bending the arm, which is comprised of multiple joints. There's multiple pieces of an arm involved. You have to reach a goal. You
can spill it.
You can spill it. It's a lot more complicated. So if we go to the next slide, you've got to see the glass. You've got to observe your environment and find the glass. You have to rotate your shoulder to get your hand in angle with the glass. You've got to check to see if you're closer, and then repeat basically until you manage to pick the glass up.
Yep.
You also have to do all sorts of things like figuring out how far away you are from the glass, updating the angle of all the joints in your arm, and then achieve the goal of reaching the glass by drinking it, which is the reward in this case.
Rotate shoulder upwards. Pull elbow inwards. Rotate wrist towards face. More. More.
Okay, so that was possibly a bit harder than we anticipated for poor John. We're going to bring this into our game.
Such a good sport.
He's such a good sport. We're going to bring this into our game engine now and take the idea of bending physical joints and train a robot how to walk.
Okay, so let's train a robot how to walk. What's involved in walking? Let's have a think. So you have to bend your hips, knees, and ankles. And to make that easier than a bipedal structure, we've made a little robot that looks like a spider, and we've given it legs. It does, you'll note, have a forward on its head So it does face a particular direction, but just having uniform legs makes it slightly easier. They don't have to worry about falling over. They can only flip. But we're going to teach it to walk towards a target object. So it's not just learning to walk forward. We're going to move the thing around so it learns to walk towards that thing and actually has that association. So we're going to go back to our observations, actions, and rewards framework. We're going to give it the observations of it knows the position of each part of each of its legs. It knows the angle and the velocity to the target that it's going for. So it doesn't really see so much as it just sixth senses where the cube is. And it also knows distances to nearby objects, so if there are other things that you can collide with in the way. The only actions that it has is to change an angle of any joint. So that means that, if you did, you can bend your knee, you can bend your ankle. I'm doing it with legs that you can't see, so that was stupid. If you were moving your arm, you can move this joint, you can move this joint, you can move this joint. And then the rewards it gets are if it's facing the target with its little face, and if it's moving towards the target, which means that it would also get rewarded if it was running backwards towards the target or if it was facing it and moving it away, but hopefully it will learn to do both.
It's basically a spider that knows the exact angle of every one of its joints. It has one of those like laser measuring things mounted to its head, so it knows exactly where the thing it's trying to get to is, but it can't see anything, and it can get a reward when it faces the target and moves towards the target.
Yes, it's kind of like echolocation, I guess, if it can sense how close something is.
I believe we have something very similar, which we call eyes. I don't know why we're going with such complex examples when we have these things called eyes.
Then you think cameras. It doesn't have cameras.
Sorry, orbs, not eyes. My bad.
It doesn't have cameras, which is what eyes would imply, but also it doesn't have depth. It doesn't have inferred depth information. It has actual depth information. That's why not eyes.
It's just got better eyes.
Anyway, we're going to teach it to walk towards the cube good. Anyway. So training this thing with 8 legs took about 4 hours on John's laptop. It's basically running at 100 times speed here, which is why it looks a bit blurred. And it starts out making those random motions as we were talking about before, where it would just be like jittering. Spider warning. Eventually it learns how to stand, so it starts flipping itself over. And then over time it will walk, run, eventually turn around, which is a much more complex thing when you've got 8 arms that you need to kind of bend some, like steering a ship. You need to do different actions on both sides. And also, eventually you start seeing emergent behavior where it learns to do things like jump, balance on 2 legs if it kind of needs to go around something. And we have seen it do a somersault where we couldn't really tell if it fell over and then managed to save itself really well. It also climbs over objects.
Here it is moving. It's quite spidery. Sorry. This is the training, I think.
Look at it go!
So
Cool.
yeah.
All right, so back to our tensor board, we can see that as the robot trains, the amount of reward it's getting increases, which means that theoretically it's getting better at doing the things that we gave it to do. And it's just as simple as that. The number is going up over time.
Stonks.
This shows about 4 hours. It is
It's
exactly
also worth
stonks.
pointing out, it actually follows a very, very similar curve to the earlier robot in that it starts off like it doesn't really know what it's doing, very flat down the bottom. Then it sort of works out a little bit, goes up, then hits sort of a maximum where it goes like, okay, I can't really get any better than this. I've sort of hit a peak of
So
my
if it gets any
walking
better,
ability.
it's like a one-time occurrence fluke. It's not going to systematically get any better.
It follows a very similar curve to our much simpler robot from before.
Yes. Next demo time.
Next demo.
Yes.
Okay, so we're back in Unity here. We've got a slightly more complex scene here. It's pretty much a similar sort of setup though. We've got our robot. In this case, it's a lovely little spider now, instead of the, what was he, Beepo? I believe the John Bot 9000.
Spyro.
Spyro. I like Spyro. And it has an orange cube here as well, which it also wants to reach. This is the goal that it's after. So, there we go, orange cube. That is its goal. And it's going to be walking around. It's exactly the same sort of scenario. We have made one small difference here beyond just the obvious one of now multiple legs. And the main difference is now the cube will move around. The reason we're making the cube move around in this one is because if we just put the cube in front of it and it had to learn how to go forward, it would just learn how to walk forward. It would never learn how to turn. It would never learn how to deal with anything else in the way. So we have the cube move around. The cube is just moving randomly. It just sort of, it
So
picks
it
a spot,
respawns every time
goes
it's
there,
touched.
moves. There's no sort of intelligence to the cube. There's nothing magic there. It literally just picks around a spot and moves. There's something I want to point out that's a little bit interesting in here. So I'm just going to zoom out a little bit here. You might notice we've got lots of these here. We actually have 9 of them. The reason we're training 9 of them is purely just because it's a performance thing. If we've got lots of them, computers are pretty powerful, we may as well train 9 of them at once instead of training one of them 9 times, sort of thing, is the main sort of idea. So it just makes it a little bit faster and a little bit easier on us to train it like this. So this is a pre-trained one because, like we said, 4 hours. I mean, this is online, so I guess we could click it and then go get a cup of coffee, big
Here's
cup
one
of coffee.
we prepared earlier.
Here's one we prepared earlier. So I'm just going to click play here now, and we can watch him walk around.
We always call them him, which is very strange of us. But
Yeah, because it's like not only is it not a he, it's not even
a robot. It is not
alive. So we can actually sort of see it walking. It's actually, you see it's chasing the orange cube there. There's a couple of things I want to point out here beyond just its terrifying
horrifying,
nature.
It is really just, yeah.
These
Very
values,
scuttly.
these values up here, the facing and approaching, tell it basically how many rewards it's getting for its facing. So this is the minty equivalent. So currently it's getting like, 1 minty equivalent reward for facing forward, and it's getting about 5 minty reward for charging forward towards it. So we sort of balance the rewards in that respect, so you get more rewards for going closer and closer to the cube, even if you're sort of facing the wrong way. So it can you'll occasionally watch it sort of like bounce side to side instead of just going straight forward, because you get more minties that way. The real reward in life is the orange cube, not to just face to it. So you want
we all
both
seek
sides.
the cube too.
We all seek the cube. You want to
You
face
can
the cube
basically hear it.
and
It's like,
move towards it. And you can see it's actually it's really quite good at this. Like, I mean, it does a few sort of like weird things that you like. It bunny hops almost a lot. And now, if anyone in the audience has ever played a video game, I don't know if that's the case, you probably bunny hop a lot in the video game as well. And that's because it is actually more efficient. Like, it's faster. You do actually move a little bit quicker when you're jumping around. That's why it sort of bounces a lot.
Zelda effect.
The Zelda effect.
Zelda
The
effect,
reason you don't do that in real life is because we have to burn energy to do that. Oh, sorry, your Paris has got the he's got the mega brain, so yeah, he just bounces anyway. Mega brain doesn't use up energy
I
apparently.
love this when you employ this method to something that is bipedal, which we didn't do here because it's hard to explain, then just like pick a joint and move it. Even though you do it the exact same way with the same programs. But if you get a little bipedal person looking thing and you go, learn to run forward, and it gets rewarded for running forward. What it eventually learns to do is it kind of punches its way forward as it runs, does these big windmill punching arms, because it propels itself forward, and it doesn't have any concept of conserving energy, so it's just like, whatever, let's do this.
So I mean, it's worth pointing out, if you really wanted it to feel much more biological in its movement, you could
give it an energy
You could
cost,
give it an
yeah.
energy cost. You'd be like, hey,
Yes.
every time you make a movement, that costs a little bit of energy.
Well, it's like when you
to
make
do
a
so.
maze solving algorithm, you don't just reward it for getting there at the end, you pick the least cost.
The only constraints of this
Much
thing
the same.
are the rewards it's getting for facing and approaching. So if you also gave it 100 energy points and you told it got rewarded for reaching the cube or facing the cube or approaching the cube while having the most of that 100 still remaining, it would try and economise, and it would eventually learn to economise those points and achieve the same goal while not moving as much.
Or it would find a glitch in the physics system where it can just like jitter on the and then warp through the floor, which occasionally happens.
Yeah, if there is a way to cheat, the AI will find it. We're pretty sure we made ours so it can't cheat.
This can get into a state where it rams it into a corner.
Oh,
And
okay.
it keeps it there because it maximises the reward.
Okay, until eventually the cube resets,
Yeah.
and then, alright, okay, interesting.
Interesting.
Anyway,
Still thinking about
on.
that AI that was told to like beat a level of a game, and it learned that the fastest way to do that was to crash the game, so it learned to exploit memory.
If you program the wrong constraints into your AI, it will learn that when the simulation ends, the reward gets total mortality or something. So the quickest way to finish is to end the simulation.
game,
If it has access to something that will end it, it will do that. It's not, you're not training it to actually reach the cube. You're training it to get points by reaching the cube.
Well, we've been calling it stupid till now.
It's not stupid. So that's brilliant, fabulous. Next thing we're going to do is we're going to give it a gun, right? This is PAX, logical, right?
Logical.
Makes perfect sense.
Logical.
This is PAX, so we figure, this is the video game things. We need to put the video game things into the robot things. It's perfect. So now we're going to go back to Tim, who's going to talk about giving it a gun.
okay, so it turns out the main thing about killing is it's actually not that tricky. Read into that what you want. So the way we're going to do this is we're going to do it a little bit interestingly. We're going to give the gun its own mini brain. So it's going to actually have two
That's what
brains
you want.
working in sync. There's going to be a gun brain and a leg brain, or legs brain. So what does the gun really need to know? The gun doesn't actually need to know too much. It basically just needs to know where the orange cube is. So first of all, we taught it where to go. Now it's just pointing towards the orange cube. It needs to know which way it's currently facing, so it can sort of work out how to aim the various gun bit, and then it's going to get rewarded for shooting, so it needs to be able to shoot. So its observations is basically where it's pointing, its actions is shoot or not shoot, and its rewards is hitting or punish for missing.
Just to reiterate,
and that's it.
Just to reiterate, the gun is a totally separate AI in this context. We're going to bolt an AI gun on top of an AI robot. They're two completely separate brains. So like it's a gun for like the Borderlands universe.
So the
It has
gun
the
can't
AI.
anticipate the spider's movements, and the spider doesn't really know that it's going towards things to shoot. I just had such a good idea that I don't know what we can do now. We should have given the cube a brain and told it to run away.
Oh.
Next time.
That is a cool idea. Yeah.
It's a good
Anyway, demo time.
Okay, so we've got pretty much the same setup here. All I'm going to do is I've made one small little change to our little spider friend here. I'm just going to sort of zoom in, not out, zoom in on it. And now there's this little tiny, teeny gun.
Fabulous.
Look at it there. So that's our little gun. It's got its own little brain. Like we said, it's following those rules. It's going to try and aim at the cube, shoot the cube. If the cube gets hit, the cube gets destroyed. The robot gets some
And just to
more
reiterate, the
rewards.
brain on the gun and the brain on the robot are not actually talking to each other.
They have no knowledge. So I'm just going
It's
to
like
play
you got
here.
a really murderous robotic prosthetic arm.
Wasn't that a Simpsons episode?
That was a movie.
Movie, okay, right.
Look at it go!
So as we can see here, so we're still sort of giving it the previous rewards, but if you notice, it's absolutely annihilating these cubes. Like it is just destroying them
Blood is
really
thirsty.
too quickly.
Bye.
So I'm just sort of gonna zoom out a little bit here so you can see it a little bit better. I'm just gonna change this sort of view a little bit here. There we go. So we'll just watch this one here. And as you can see, it's actually destroying the cubes. It's destroying them sort of within about 3 seconds of the cube reappearing. So a cube's popping up, the AI is detecting it, it's moving its gun and destroying it within seconds. Like it's absolutely terrifyingly fast how quick this thing is just annihilating these cubes. So if you're an orange cube, be very afraid.
Duplicate
basically.
the robot?
Not
It
horrifying
is already
at all.
duplicated.
No, in the one scene.
Because they won't acknowledge each other, and then they'll both just fight over murdering the same cube, but they won't know
can,
each other
but it's-
exists.
Not really worth trying to figure
They'll
that
just
out.
be like, I want to kill it. No, I want to kill it.
That was, oh god, duplicated the whole platform. Where is there? It
Just
is.
duplicate the robot. And
Yeah, no, there we go.
come back. So we're just going to duplicate the robot and show you what happens when there's two of them, because they have no knowledge of each other, but they have...
Three of them now.
Three of them, more of them. They have exactly the same brain feeding into them all, but they're all trying to accomplish the same.
They also can't see each
But they don't know
other.
anything
so-
about each other at all.
So
But the physics system probably will let them interact.
just gonna, here
They'll
we go.
just crawl all over each other to murder the cube.
It's going to be great. Yeah.
Look at them go.
Yeah.
Closer, closer.
That's 4.
Oh, yeah.
So they're all-
That makes them extra spidery, actually. That's freaky.
Yeah, it's really quite freaky. So you can imagine if you're using this to build like a video game AI, you can make it once and then just duplicate it. So that's horrifying.
I think it's alright.
Should we return to the slides and continue?
So now that what we've just learned is that robots are just fantastic at murder.
And spiders are still terrifying.
That's right.
The more horrifying than ever, yeah.
More horror, totally disgusting.
That's great.
So they will be the death of us all.
Hopefully.
That's really cheery.
If we
So-
program them well, yes.
That's right, exactly. Unless we can find one gold pilot to turn the tide, we're completely lost.
Yeah, who could that be?
Who could that be?
Oh, it's Meredith!
Yay!
This is not going to end well at all. I apologise.
Demo time!
So we've connected this Xbox controller to a small robot.
So if we jump into Unity here, I'll here's our little robot here.
So it's actually the robot from earlier, little beeper, but with a gun.
Oh,
yeah.
cool.
So as with all things,
So you don't have to learn how to skitter.
adding more guns. So we've decided to make this so you don't have to walk, because I think it's tricky enough. Poor Meredith's going to have to fight this thing, let alone having to also figure out how
We're
to
also
walk.
lazy game developers, so we just took one of our existing assets and bolted a gun to it.
Yeah.
Either way, it works in a very similar fashion. It has a gun that can be independently moved of its body and aimed, and then it has a shoot ability. Much like with the robot, if you successfully hit the cube, you will get a point. The robot hits the cube, it will get a point. It's the exact same robot from before.
Okay.
It's a very similar arena to before. The only difference is we've got this lovely like little scoreboard.
And you'll
up
see
here,
we've
which-
optimistically made a humans
so
win.
optimistic.
Very optimistic.
It's the last time I'm going to see that.
That's just because we coded it correctly, you know. Like we,
So
you know,
there is a win state for humans in this game, so we did this properly.
Cool.
All right. So,
There's even a UI element.
Yeah.
are you ready, Meredith?
Humanity's off, hope, no pressure.
I'm going to turn on the spider.
Oh.
Go. All right. So the spider is currently 2-0, 3-0,
3-0,
4-0,
I'm actually
5-0. All right. You
bold
can do
effort
it.
to point at the
Whoa,
cube.
oh,
Oh, the spider's down.
The spider fell over. This is your. Oh no!
No.
It got back up.
Right.
Yep. Never mind.
There you go. Okay, no.
Am I shooting forward?
Just
Yeah,
follow
you're
the
shooting
spider.
Good.
Just take the
Okay.
spider.
Oh, never mind. There's still 1 minute and 7 seconds. You can come back from 13 down. I'm sure.
okay, fire.
Oh no, 15 down.
Just
It's alright.
keep firing. Fire as fast
Yes,
as you can.
you
Yes!
Humanity has a chance. You've only got to get another 20 more points and make sure it gets 21
sure.
more points and
Sure,
makes
you can do this.
22,
You've got 50
23 more
seconds left,
points.
so you can do this. You
We
can come
believe
back
in
from
you.
this.
You are the last hope for humanity. So like,
But you can't shoot the spider.
Yeah, that would be fun.
You could probably run into
Yes.
oh, the
Yes.
spider!
flip it over or something.
It's actually worth pointing out the spider actually shot that cube as it was falling over.
It's
very
So like,
good.
it's very
The
good.
gun
Like,
don't care what the legs are
because the
doing.
gun don't care.
Yes. Oh.
Oh, you're so close. Come on. It's only up by 33 points, and you got 25
do
seconds.
it.
Actually, it
can
can't
do- oh.
shoot the cube because it will be behind a rock. So that's the trick.
Oh, and the spider
Yeah.
fell over again. This is good. This is good for humanity. Oh,
The cube can go through rocks.
you can get it. You can get it. Ah, quick. No.
No.
Yeah. Quick. Fire. No.
Four.
Yes, you got it.
Got it. Yes. 3, 2,
Oh, come on.
4. Hey. This probably wasn't fair because like
I'm not
The
surprised.
robot was allowed to use 2 brains.
the robot had 2 brains. Meredith only has 1.
But the robot's brain is much smaller than Meredith, so I don't
Yeah.
know. Like both of its brains combined are nothing compared to a human's brain. So something that's very interesting here and always worth pointing out, I think, is it's worth showing the robot is still just killing. That's because it does not care. The robot has absolutely no understanding of the world around it. All it knows is shoot cube and run towards cube. Which means even though the game has ended and it has won by a phenomenal 35 points over Meredith, it doesn't care. Its sole objective is to keep annihilating those cubes, and it is still keep doing it. So it's something that's really interesting. It doesn't understand anything except kill cube.
You kill cube.
You kill cube.
my
You
God.
kill
Thank you.
cube. It is
So
very
obviously
good at
that was
though.
slightly unfair on Meredith because the robot is just an unstoppable death machine. But
Great.
none of us except for Tim are very good with a controller, so
That's true.
we did deliberately choose.
Mars
one of
did
us-
pretty well with it.
Well, Mars did okay last time.
Yeah.
I would have done as badly as Meredith did, to be honest, because I just can't use a controller at all.
The point is, all hail our victorious robot overlords.
That's right.
So
What can we learn from this then?
something, maybe.
Hopefully.
Can we learn something?
Yeah.
So this is basically what's called a Skinner box, something which has been used by animal experimenters
Yep.
to study behaviour conditioning, so training,
Yep.
by teaching a subject animal to perform certain actions. So in this case, like pressing a lever, for example.
Yep.
So in response to specific stimuli, such as light or sound, when the subject correctly performs that behaviour, the chamber mechanism delivers food or some other or
A minty. A cube.
in this case as well. That's right.
And the little John in the box goes, yay!
This John is a
The John in
mouse.
the Skinner box is a mouse.
I like how we're just continually degrading John further and further and
It's
further.
fine, he's in the field.
Yeah.
That's true, he's out in the field.
We left him in the
We can
park.
say anything we want about John because he's not just over in the corner there.
He's not behind the
yes.
camera.
Not nowhere there.
Hi, John.
Hello.
He's in the field.
Anyway,
So
Skinner box.
Yes.
But really, AI isn't that clever. Because AI is just learning by doing, and this is our little punchy man that I was talking about before. It doesn't have any other context about the world. It only knows what it's tried before and been rewarded for. It doesn't have any morality. It does not care if you've missed the cube, if the cube was humanity's last hope. It's only learning by doing.
And unlike the Skinner box that Meredith just mentioned, it's perfect. Like, a rat can just ignore it and do something else, whereas this is never going to ignore it. It's always going to obey the rules of the Skinner box.
It's as if the world that you give it is its everything, far more so than any biological entity could ever hope to be as obsessed with an orange cube.
Yes.
Yeah. So learning actions to do guided by observations and then rewards,
Yes.
essentially.
Thanks to John. Yeah.
Thank you,
We
John.
left him in the
Thank
park.
you, John.
We left him in the park though, so yeah.
So thanks everyone. If you see you later.
Bye.
If you have any questions, you can tweet at us the above handles. We're using the hashtag PAXAI.
Yes. Thanks for watching, everybody. Hope you enjoyed it.
Thanks.
Thanks. Bye.
Brilliant.